Welcome back. This lesson is about attenuation. When an X-ray beam passes through matter, like through a patient, there are three things that can happen. Some photons are transmitted all the way through the patient. We just call that transmission. Some photons are absorbed in the patient, so we call that absorption. And some photons interact with the body and are scattered out of the beam, and so we call that scattering. Absorption and scatter remove photons from the X-ray beam, and that's what we call attenuation. Attenuation is specifically defined as a reduction in the X-ray beam intensity as a result of absorption and scatter in matter. To understand attenuation, we really have to understand intensity. Remember that intensity refers to the number of X-ray photons. Before passing through matter, the X-ray beam will have a specific intensity. We call this part of the beam the primary beam. When passing through the patient, a number of these photons are removed from the main beam because of absorption and scatter. In other words, they're attenuated. After the beam leaves the patient, we call the attenuated beam the remnant beam or the exit beam. It's kind of like shining a flashlight through a piece of paper. Much of the light striking the paper will be absorbed or scattered out of the light beam. And this is the idea of attenuation. The remnant light beam is less intense after passing through matter. With an X-ray beam, attenuation is the result of some very specific interactions: photoelectric absorption, coherent scattering, and Compton scattering. All of these interactions occur in different proportions with every X-ray exposure. These interactions are discussed in detail in other videos, but here's an overview. With photoelectric absorption, the X-ray photon enters an atom in the body, and the X-ray photon is completely absorbed by an inner shell electron. This results in the electron being knocked out of its orbit, which is called ionization. So in this mechanism, there's a photon in and an electron out. This interaction removes a photon from the beam. So photoelectric absorption contributes to attenuation. That's a decrease in beam intensity. The next interaction process is very different: coherent scattering. With coherent scattering, the process starts the same. An X-ray photon enters an atom in the patient. The photon is initially absorbed by the atom, and then the energy of the photon is ejected out of the atom as a photon with the exact same energy, but in a different direction. No ionization takes place. The photon is only scattered, meaning it changes direction. So in this mechanism, it's a photon in and a photon out. Coherent scattering can also result in attenuation if the photon is scattered completely out of the beam. The next interaction is Compton scattering, and it's kind of a combination of the two. As with all interactions, the X-ray photon enters an atom in the patient. This X-ray photon is only partially absorbed by an outer shell electron. This results in the electron being knocked out of its orbit, again called ionization. The remaining photon energy, though, is carried away by a scattered photon. So, in this mechanism, it's a photon in and both an electron and a scattered photon out. Compton scattering can result in attenuation if the photon is scattered completely out of the beam. So how often do these attenuating interactions happen? Well, the amount of attenuation is actually dependent on a few things: part thickness, tissue density, atomic number, and beam energy. Let's start by talking about the part thickness. As part thickness increases, attenuation increases. In the upper image, we're dealing with some part of the body that has less thickness. If there's less thickness, that means there's less total matter that the X-ray beam has to go through, and when there's less matter, there's going to be less attenuation, because there's not as much stuff in the way to attenuate the X-ray beam. But if we X-ray a part that has more thickness, this means there's more matter that the X-ray beam must go through, and in the end, this results in more attenuation. Another factor that affects X-ray beam attenuation is the density of the parts we're imaging. Here's an example. The chest and the abdomen have just about the same thickness in most patients, but the abdomen attenuates significantly more radiation. Why is that? The chest has less density. That means there's less stuff inside the same volume of tissue. If there's less density, that means there's less total matter, and if there's less matter, that means there's less attenuation, because the X-ray beam doesn't have to go through so much material. In the example of the abdomen is significantly more dense. That means there's more material or more matter packed into the same amount of space. If the X-ray beam has to pass through more total matter, that results in more attenuation. Another factor that affects X-ray beam attenuation is the atomic number of the materials we're imaging. For example, in this radiograph of a hip, the soft tissues attenuate a minimal amount of radiation. Soft tissues have a relatively low atomic number. That means the nucleus of the atom is very small. Minimal attenuation means that most X-rays are passing through the soft tissues. Bones, though, attenuate more radiation because, on average, the materials in bone have a significantly higher atomic number. And in this example, the metal implant in the hip attenuates the most radiation. That's because the steel hardware has a very high atomic number compared to the bone and soft tissue. The density of the metal is also a contributing factor to increased attenuation. The last variable affecting the amount of X-ray attenuation taking place is the energy of the X-ray beam. In this example, a low kVp X-ray beam results in less energy in the photons. Less energy results in less penetration. The photons don't have enough punch to make it all the way through the material. And if there's less penetration, that means we have more attenuation. The X-ray beam intensity is decreasing significantly as it passes through matter. Compare that to the high kVp X-ray beam. High kVp results in more energy in those photons, more penetration because they have enough punch to make it all the way through, and that results in less attenuation because more of those photons are passing all the way through the patient. In summary, understand that attenuation is defined as a reduction in X-ray beam intensity as a result of absorption and scatter in matter. X-ray beam attenuation is the result of some specific interactions, especially photoelectric absorption, but also coherent scattering and Compton scattering. The amount of attenuation taking place is affected by these variables: part thickness, tissue density, atomic number, and beam energy.